We continue with graphing techniques. In 15D, it will be about ellipses. First is the how do you define the locus? Is to do that, what you're gonna have is you're gonna need two fixed points. Those two, F1 and F2. Each one of them is a focus. Plural is foci. And what you have to do is the distance from a point P from each focus point, the sum is equal to a constant. So the idea of it, as that length is constant, that will lead to how to draw it later. Just below is, imagine this is a piece of string, you link it to two fixed points, you get a pen at that end, and you move it along around. So that what leads to how you construct it down here. So you would use two pins into a piece of paper. You will have a fixed length k of a string. You'll tie it up, and what you do is the tip of the pen, you would pull the string straight to maintain that length constant and to form a triangle, and you move it out along, and all you will form the curve that is the ellipse. So you will need to apply that through algebraic resolution. So we'll do that in an example later on. Now you might have recall the Cartesian equation of an ellipse. So an ellipse can be let's go backwards. A circle is a particular type of an ellipse. So if you remember the equation of a circle, the equation of an ellipse will kind of be similar. Now, what you have is those terms divided by those constants that are expressed in a square form. That will be equal to 1. Those values will determine the intercepts along the x and y axis. We can also apply a transformation to two translations, across and vertical. Across is h and k. That will tell you the coordinate of the center of the ellipse, and similarly you will have the not the intercept this time, but the the left and the right hand side, as well as the up and down parts of the ellipse. So that will be the denominator of the each fraction squared. So let's look at a situation where we'll do a little bit of an algebraic resolution, which is quite of it's going to be interesting to manipulate, because you're going to have an equation that will have multiple square roots, and this is a strategy you need to be using at all time when you want to try to solve those kind of equation. So here you have two fixed points, A and B. The coordinates are given to you. Find the equation of the locus of point P satisfying this equation. So the sum is equal to 8. So you need to express the distance AP and BP, knowing you have all the coordinates. The coordinates of P are going to be variables x and y. So we express that the distance between 2 points, you have two square roots, and what we need to do is to get rid of the square root. What we used to do is, when you have a square root on one side, on either side, we just square the whole equation. Now at the moment, the way it is, if you square all of that as a perfect square, you have two terms that will be squared of those, which is fine, but you also have the twice the product of those two that will still give you a square root. So the strategy here is, what you do is you isolate one square root, it doesn't matter which one, on one side. So let's say we keep this one and we transpose the other one. So now we have one square root on one side. Now you square the whole equation. The left hand side is here. The right hand side gets a little bit more complicated because it's a perfect square that you expand and you regroup the like term as much as you can, which is what you have here. You expand the brackets. Now what you need to do again, you have a square root here, you need to isolate it. So anything that is not under the square root, you transpose on the other side. That's simplified to that expression. And now you have a single square root here. There's a coefficient, which is not a problem. So what you do now, you can square that whole equation. Now you square both sides, you get this new equation. You need to expand it and regroup the like term. That simplifies to that. We like it for an ellipse to make it equal to 1, so we divide by 48. You get those two fractions. They are 16 is a perfect square, so that's 4 squared. That's linked to an x, so that will give you on the graph a -4 and a 4. That will be your x-intercepts. And on the right, that's a 12, so when you square root that, that's positive plus or minus 2 root 3, and that's what you get vertically upwards and downwards. And that will be the locus of a point P that will fit this formula. Alright, now you have another situation, so it's to find the equation of the locus of point P xy. I'll let you read this. Try to come up with the original equation, so read the information carefully, pause the video, and we'll come back to this. Alright, so it says the distance from P to point F with the given coordinates will be half the distance, so it will be equal to half MP, which is what you have down here. F is your focus point, P is your variable point, the one you need to find the locus. Half of MP, again, you have in terms of your variable point. Now what M is, and that's what you need to figure it out, it's, you know, MP is the perpendicular distance to the line with equation x equals -2, which is a vertical line. So you draw a vertical line, x equals -2, and from P you will project a perpendicular line, so that line MP needs to be right angle. So here, for any point P, that's your vertical line, you project it, so you have a right angle here, that's your M point. As it is projected along here, it will have the same y coordinate, and the x coordinate, because it is on that line, it will be -2. F is a fixed point, so that's the fixed coordinates, and we get that nice equation. So now we know the coordinates of all the points. We can express FP and MP as using the formula between 2 points, which is a square root. We have a square root here, so we have square roots on both sides. You square both sides, then you expand the brackets and you regroup the like terms. Now it's not an ellipse equation yet. You have a y squared term here, you have x squared and x term, so the next step is you need to complete the square with those two terms. So as you complete the square with those two terms, you get a perfect square here. You will have a 12 coming out, which is that one. We prefer to have it equal to 1. We divide by 1, we get a 4 and a 3 on the denominator. Now it's x minus 2 under the square. Here the y squared means it implies y minus 0, so 2, 0 will be the coordinates of the center of the ellipse. And that's it for today. See you later.